Good morning, everybody. I mean, you guys have been up probably more than I have, but everyone's waking up exactly at 11. Awesome. So I'm a software engineer at Nscale. Literally just announced this on Monday, just signed the contract. So that's super sick. And I'm going to teach you stuff that if you've been to college, you've probably already learned. If you haven't been to college like me, then you're going to learn.
So one thing.
Yeah. Sick. That's my notes in case you guys want to read those.
Otherwise, you want people to know what kind.
I wish people would play like the technical difficulties music. But I have it here. Where's your... This is... Have you ever wanted to do this on a huge screen?
Relaunch the update.
Relaunch the update? Oh, almost there. Yeah. Okay, that's beautiful. I have no notes. Awesome. We're just going to try and wing it from all the notes I wrote. So in 1965, the Vietnam War started, which I know everyone here is really in tune with. New York City was surpassed as the biggest city by Japan. And then also, I live in the Netherlands, but my Dutch is horrid. So when you hear me say Dijkstra, you can all laugh and say, oh, silly American. But E.W. Dijkstra had a class of students, and he was trying to teach concurrency to them. And how he did this was by creating the Dining Philosophers problem. So nowadays, with concurrency and in Go and in Python, we have things like mutexes, locking mechanisms, and Go routines. So we don't really have to care that much about concurrency. Like a lot of this stuff is handled for us. And in Python, there's like the async package, so you don't actually have to worry about like, how do I deal with multi-threaded processes as much as you would back in 1965, right? But I think it's kind of interesting because I know how a Go routine works, but I've never had to actually solve a problem with a lot of white men sitting at a round table and trying to eat. So the Dining Philosophers problem starts like this. You have the number of forks, and in this case, we're going to use chopsticks because it works better, but you have the number of chopsticks to the number of people at the table. So we have 5 philosophers, we have 5 chopsticks. You can see where this becomes a problem when basically only 2 of our guests can eat at the same time because we only have 5 chopsticks. So either the philosophers can be in an eating phase, so they're eating, sleeping, or thinking, then they cannot talk to each other. And what we want is to get the most philosophers eating at the same time while also getting them all fed fairly. And so how do we do this, right? We need to get them 2 chopsticks at a time. And what is the problem really trying to solve? So basically, we're trying to satisfy this 4 conditions that are for race conditions here. So you can kind of see that, like, if we have 2 philosophers going to grab the chopstick at the same time, they're either going to end up holding hands, which is kind of cute, or they're going to end up breaking the chopstick. And if they break the chopstick, I guess they both could eat. And like if we broke every chopstick, then we'd solve the problem. But then we break the problem and it's not that great. So we're trying to figure out, how do they eat, sleep, or think? And when they want to eat, how do we feed them, right? How do we feed these philosophers without ending in a condition where, you know, we're both modifying the chopsticks at the same time? And so for the 4 conditions that we have to, well, you choose one of the 4 conditions to negate for deadlock. And those conditions are, I hope this next slide has it. Yes, okay, mutual exclusion. So mutual exclusion is basically saying, when we have 2 running threads, I'm gonna make it programming here because it's just easier to explain that way. 2 running threads, they can only enter a code they can only enter a critical selection at a time. So basically that's saying, critical execution is saying that you can only write to data or modify the data 1 thread at a time. You can't have 2 processes like mutating the data at the same time. Resource holding, which we've seen with like Amazon and everyone else, like you've had processes just like hold a bunch of resources, start ballooning memory, and then your servers crash over. So it's the same thing here. You cannot just hold the chopsticks forever. And then we have no preemption. So we cannot preemptively try to grab the chopsticks and then like think about it and like hold them forever. And circular wait. So a lot of these problems, the solutions go to like everyone goes to the left, to the left, to the left. But we can get to the point where we're always waiting on someone and then we don't do anything. So for the Dining Philosophers problem, you choose one of the four, which makes it a lot easier. If you choose all the four, you're not going to really solve anything. Or you might, but you'll lose your brain in the process. So we'll get into solutions. Now, Dijkstra's solution was basically to not use counters. It was to use a semaphore, a mutex, and like a simple data structure. And remember, the philosophers can't talk to each other. That's just, I don't know, because they're philosophers, they need to think. So what he would do basically is they would enter a phase where they would say, hey, I have the chopsticks, and I see that I can get a chopstick next to me. So I will pick up 2. And then when I am done, I will just put them back down. And then the person to the left of him would then enter the phase of eating and so forth. So they would be kind of like a waiting mechanism. And it would also use like a random heartbeat, if you kind of think of it like this, because we have all 5 philosophers that sit down at the table at the same time. This isn't very realistic, but all of the solutions like have the idea that the philosophers enter the table at the same time. So when this happens, he sets like a random heartbeat kind of thing so that you have some differences on when we're entering these eating phases, right? We have a couple other solutions. Dijkstra's is the only one with tests that I found, so go him. We have the arbiter solution. And if you like Halo, that's why we have the arbiter. I always wanted to play the arbiter, by the way. I always thought arbiter was way cooler than the Master Chief. So I got in a fight with my partner about this morning, that arbiter was way cooler. Anyways, so for the arbiter, it's kind of cheating, right? Because what happens is you have a waiter, and the waiter handles all the philosophers. And so the philosophers say, can I please eat now? And the waiter says, well, let me look at how many chopsticks we have, and I will go get a chopstick from someone else and move it to you if you need to eat. I need to wait for that person to stop eating and bring it over to you. This like works weird because now we're communicating with an external source. So it is like communication, and they aren't of their own mind figuring things out. But it is a little bit cleaner. The problem with this is that in distributed systems, and this all comes back to that, you want things fast and concurrent and kind of without having to rely on like a master or a leader setup, right? If you're familiar with like Raft or etcd, you have problems with like multi-master nodes where you can get like split brain and things like this. And this, what if we have 2 leaders, or not 2 leaders, 2 arbiters? What if we have 2 waiters? Or if you've had this happen, your waiter kind of like stops their shift halfway through, and then a new guy comes in, and then the bill's kind of messed up or whatever. In here, there needs to be this like communication that happens between waiters. And you also have what is now delays between the waiter having to receive the information, go, I know this guy wants to eat, going to find the chopsticks, without something a little bit cleaner where they all communicate together to find out the solution. And the next one is the more complicated one, but I think it's also the most fun. It does not use like an arbiter or a waiter or anything like that. What happens is for the number of people at the table, I have to go all off my brain pan on this one. So the number of people at the table is how many chopsticks you have. Switch it. Yes. So the number of people at the table is the amount of chopsticks you have. What happens is they are all numbered. We don't number the people, we number the chopsticks. And the chopsticks then have the timeout on themselves. And the chopsticks can have 2 states, dirty or clean. And so if you get a chopstick and you are eating, it is clean because you're eating a clean chopstick. But once you're done and someone else wants it, it is dirty. And they can request only dirty chopsticks, and you can only eat with clean chopsticks. So the transition of you handing a chopstick, I don't know, it magically gets clean to the other person. This then stops it from you going to like other philosophers and them being halfway through a meal and handing you their chopsticks before they're done eating. So the thing that makes this cool about this is a lot of the other solutions, Dijkstra's solution, the arbiter solution, either you have things where like people are waiting, or you have like an external like party you're talking to. And this is more focused on the chopsticks themselves, the resources themselves here, of how do we optimize the resource, not the nodes, philosophers talking to each other, right? So I think that's pretty cool. While reading this, I realize a lot of the times that when I think about, hopefully this resonates in Kubernetes clusters, I think a lot about like how nodes can communicate with each other and figure out how to like read data more effectively, right? And like handle and transition locks and not like bump into each other. But I've never thought of the data itself as a resource that should handle making sure it doesn't get bumped into. It doesn't get written to twice at the same time. It doesn't go and enter a deadlock. Okay. So how does this connect to real life? It's hard for me to think like, okay, like we could talk about like Go routines and like fun things with channels and that kind of stuff. But one thing I thought was really fun and still a problem to this day is, I think it was in 2019, Cloudflare updated their WAF, their web application firewall. And they had like this one line of JavaScript, which feels very CrowdStrike, it was CrowdStrike who did the whole like taking down all the airports with the update of the computers with like modifying their bootloader. Cloudflare had a WAF update that was just one line of JavaScript that would then start ballooning resource consumption because it would spawn too many concurrent threads that would not end execution. And this ended up just like starting to topple over. You can see on their graph, if you look it up, it's just like all global resources started ballooning. In the Cloudflare blog itself, it says, we are used to seeing resource ballooning, but not at a global scale. So it brings the everything back to home to say, well, if that one JavaScript engineer at Cloudflare knew more about how concurrent executions happened, could this been stopped? Probably not, but it is like, this is still a problem in our real life. Another problem that has also been seen, and I kind of, what's that word called? Shaded to it early on, foreshadowed. There we go. Foreshadowed to it early on this is a really common problem in AWS. Whenever you migrate S3 buckets, there's a lot of data that needs to be moved. While that migration's happening, you're still also doing writes. And so we're getting into problems with like deadlocking or like trying to figure out how can we move this data without handling a lot of people having a thundering herd onto it, but also being able to still leverage it. So lastly is like, this is kind of a weird problem, right? How do you deal with 5 dudes trying to eat dinner with 5 chopsticks without holding hand, breaking them, and also making sure everyone's fed in fairness, but they can't talk? And I think it's really cool to see the solutions that people are coming up with on whether it's like dealing with timeouts, whether it's implementing heartbeats, whether it's putting conditions and states on the chopsticks themselves or the people themselves. In Jaiksha's solution, he only put the conditions and states on the philosophers themselves, and it was like a enumerated state, right? So I think it's fun to take this home and go like, how would I implement this? If you like HackerRank or haven't seen this on LeetCode, but like HackerRank or something like that, this would be like a fun problem to sit at home and do yourself, especially because you can figure out the test cases really quick and then watch yourself fail for a couple days. And then also like, is this something you could take to your job and you've seen yourself? Have you seen all these like resource ballooning issues? Have you entered a condition where you implemented deadlock? I've myself have also forgotten to open and close a mutex in certain areas. And so I've also been the problem. So yeah. Thank you. I talked really fast. I'm sorry.
You were definitely the speediest speaker so far. Yeah.
I thought I was going to talk slow.
No, but the good news is this gives us a lot of time for questions. Yeah, and we got the mic runner and the Haribo runner. So who has any questions? Questions. Come on. Don't be shy.
You can ask them.
You can ask them questions, yeah?
Yeah.
You know,
Now I can't make fun of them for not having questions if I don't have one. So have any of you dealt with a problem with concurrency like this in your day-to-day? Let's get that guy.
Putting on the spot.
I know. Now you're the speaker.
Thank you. I'm working on a real-time queuing system, and so we have a lot of messages going on in flight at the same time, and it's not fun.
What is the kind of problems that you're seeing with this type of solutions that you're implementing?
As you were saying, like forgetting a mutex in a specific place, or things like that.
Yeah. That sucks. I've done that a bunch.
Is AI going to save us?
AI is, yeah.
No.
Oh, unanimously agreed. Has anyone else kind of come into a problem? Oh, yeah. Question.
Bad.
So I think the tricky one is when these problems come up only every blue moon or not all the time. So how do you test to see if you have an issue like this in your application, if it's not obvious?
I think it is kind of obvious when people don't note it. So when I was working on the Raft database, we had a lot of flakiness, right? And you would see in like Circle CI or something like that was like 70% flakes in your testing, which was awesome. And I thought it was just because of timeouts. But the actual problem the flakiness was showing was that we had a bunch of race conditions that we weren't detecting. And we, at that time, the go test race flag was still there. So we were able to test it that way and go, oh yeah, like, look, here's all our flaky tests and modify it. But I think there's symptoms that we generally ignore that are pointing to the problem. And it is things like flakiness, or it is things like you're having a bunch of servers spin up and topple over and you're just kicking it over and over and over again, which I'm very familiar with, as like, just like, don't treat the actual problem, just treat the symptoms. So I think that's what I see. Did that answer your question too? Okay, good.
Anyone else?
Does anyone else think AI will fix this?
If somebody says yes, I'm going to scream. No, the obvious solution to most of these problems is, of course, the thing that we mostly use is mutexes or semaphores like that. Have you ever run into the problem that those are actually too slow for the thing that you want to implement because the speed of the execution of the threads or the multiplicativeness of the threads is too much that the mutex is actually slowing you down instead of speeding you up?
I mean, I haven't, but I can see what I would respond to that with is like, basically, I've found that there's a trade-off here between consensus and concurrency, right? So you can either be right or you can be fast. And so in this case, it's like, yeah, you can handle like a bunch of like reads on this data and like it can be wrong like 50% of the time, or you can be fast or slower and right. But it really depends on your application. And I've found that most people don't want to be wrong. They would rather be slower and correct than faster. And that's kind of like the antithesis of like what I want to do.
If you're implementing business cases, yes. If you're implementing games, mostly no.
It's true. Yeah.